Hi guys, welcome to video lectures of DST classes. In this class, I am going to explain about combinational circuit designs, Boolean algebra and gate level minimization. So to design any combinational circuit or the analysis of combinational circuit has to obtain the output Boolean functions from a logic diagram. The procedure involves the following steps. So to design any combinational circuit, so one is label all the gates outputs with unique symbols. So we have to label all the logic gates and OR. And second one is find the Boolean function for these gates. So whatever the logic diagram we have, so we have to first step is nothing but we have to give unique names, symbols and or XOR. And then we have to write the out Boolean expression. If we have any AND gate, what is the output equation? C equal to A and B. If we have OR gate, C equal to A plus B. So we have to write the Boolean function. And to obtain the truth table directly from the logic diagram, the procedure involves the following steps. So using the truth table also, we can draw the logic diagram. So for that we have these four steps. So one is determine the number of input variables in the circuit, and second one draw the table for these inputs. There are 2 power n combination for the n input variables. So if we have 2 inputs and possible combinations are 2 power 2, 4. If we have 3 inputs and the number of possible combinations are 2 power 3, 8. Okay. So if number of inputs, how many number of inputs, and then the combinations are 2 power n. So next third step is label the output with unique symbols for the gates in the circuit. So whenever number of gates output for these all outputs, we have to give the unique symbols. And fourth one is obtain the outputs of these gates in the tables. So next step is nothing but the obtain. So these are the 4 steps. So from directly we can draw the logic diagram using these truth tables. So next is Boolean algebra. So Boolean algebra is mainly used to minimize the Boolean functions. So one of the important function of VLSI is we have to reduce the area size. So area, as reduce the area, we can increase more number of components on that IC. So for reducing the circuit complexity or number of components in the block diagram or logic diagram, first method we have is nothing but Boolean algebra. So using Boolean algebra, we can minimize the Boolean functions. So Boolean algebra is used to analyze and simplify the digital circuits. It uses only the binary numbers, that is zeros and 1. So one more important point in Boolean algebra is, so Boolean algebra we use only zeros and ones. Except zeros and ones, we cannot use other digits. So it is also called as binary algebra. Why? Because we use only binary numbers. Boolean algebra was invented by George Boole in 1854. So from 1854 we have Boolean algebra. So we have to follow some rules to minimize the Boolean algebra, Boolean equations. So these are the 4 basic rules to simplify any Boolean equation using Boolean algebra. First one is variable used can have only 2 values. So I already mentioned Boolean algebra we use only binary numbers which are nothing but zeros and ones. Here also variables used can have only 2 values, binary 0 and binary 1. So binary 1 is for high value and binary 0 is for low value. And second point is complement of a variable is represented by an overbar. So a bar, we can write a number or a bar. So then thus complement of variable b is represented as b bar. Thus if b equal to 0, then b bar equal to 1. And if b equal to 1, then b bar equal to 0. So just it is a complement. Complement means if input is 0, then output is a bar. If a is input, then output is a bar. If a is 0, a bar is 1. If a is 1, a bar is 0. That is complement. Second rule. So and third rule is nothing but, so basically digital circuit we have 3 basic gates. What are those 3 gates? NOT gate, AND gate, OR gate. So second point is nothing but NOT gate, complementing. And third rule is nothing but using OR. ORing, what is OR? OR gate, using OR gate. So OR gate, what is the output of OR gate? If any one input is 1, output is 1 for OR gate. So in OR gate, output is 1 when only both the inputs are 0. Remaining all condition, output is 1 for OR gate. So ORing of the variables is represented by a plus sign between them, a plus b. For example, ORing a, b, c is represented as a plus b plus c. This is the ORing. So next fourth is nothing but logical ANDing of the two or more variables is represented by writing a dot between them such as a dot b dot c. Sometimes the dot may be omitted like a, b, c. So a, b, c is ORing between three inputs. So sorry, ANDing between the three inputs. What is AND? AND is nothing but output is 1 when and only when all the inputs are 1. So it is nothing but the dot products. So we have to follow all these three rules. So first one is only binaries, zeros and ones. 0 is logic 0, 1 is logic 1. And second one is complementing, where if a is input, complement of a is nothing but a bar. If 0 and output is 1, if input is 1 and output is 0. ORing is nothing but addition of the inputs. So a plus b plus c, we can write like this, a plus b plus c. If any one input is 1, output is 1 for OR gate. So next one is but nothing but ANDing. ANDing is nothing but dot product. So these are the Boolean algebra rules. So these are the Boolean algebra theorems. So law of identity. Identity name itself indicates that identity means if A, then it is equivalent to A. If A is 0, output is 0. A is 1, output is 1. This is identity. So next one is nothing but the complement. A bar equal to A bar. So same inputs are whenever input is equivalent to output, then that is nothing but the identity law. So next is cumulative law. So A dot B equal to B dot A plus B equal to B plus A. And then third law is associative law. A dot B dot C equal to A dot B dot C. And A plus B plus C equal to A plus B plus C. So next idempotent law. A dot A equal to A plus A equal to 0. So identity, so whenever A is 0, 0 into 0 equal to 0 or 1 into 1 equal to 1. So A into A equal to A. So 0 plus 0 equal to 0, 1 plus 1 equal to 1, ORing function. So when both the inputs are same, output is also same. So next double negative law. So A double bar is nothing but A. So A bar is if 0, 0 bar is 1, and if we complement second term A double bar, we will get the same value as A. So next is complementary law. A dot A bar equal to 0, A plus A bar equivalent to 1. So these are the some of the rules of Boolean algebra theorems. So these are the theorems are x plus 0 equal to x, x plus 1 equal to 1, x plus x equal to x, x plus x bar equal to 1. So all these rules are called as OR gate rules. So next is AND gate. X dot is nothing but the AND. So x dot 0 equal to 0, x dot 1 equal to 1, x dot x equal to 1, x dot x equal to x dot x bar equal to 0. These four are ANDing. So next these are the properties, so as I discussed now. So x double bar equal to x, so cumulative x plus bar. So these are the, and the last theorem, De Morgan's theorem, is very important theorem in Boolean algebra. So it will state that x plus y whole bar equal to x bar dot y bar and x dot y whole bar equal to x bar plus y bar. So these two. So to simplify any Boolean equation, first we have to concentrate whether Boolean algebra's theorem, De Morgan's theorem, is applicable or not. So first we have to apply De Morgan's theorem. Then using all other theorems, we have to simplify any Boolean expression. So we have to reduce the number of components or number of gates, or we have to simplify the Boolean expression using Boolean algebra. So how we can how we can use Boolean identity operations in VHDL. This is an example how we can write the VHDL code in Boolean identity. So these are the x is input, y is also input. This is the x is a scalar type, whereas y or is a vector type, y and is a output. So we have two outputs, r and ANDing, r function and ANDing function. So these two are vector type. And constant 1 is STD. So this is nothing but the how we can define a constant in VHDL. Any constant, start with the keyword constant followed by constant name. Here the constant name is 1 colon type. So it is 1 is type STD logic and the value of 1 equal to, so 1 is nothing but 1. So 0 is the name of the other constant. the value is 0. So here we have to define our content statements. So first 4 are nothing but the OR functions and last 4 are nothing but the AND functions. OR, X OR 0, X OR 1, X OR X, or X OR not X. So next is nothing but the AND. So these are Boolean operations, how we use Boolean operations in VHDL. So next is nothing but the gate level minimization. So we use gate level minimization in using K-map. So gate level minimization aims to simplify input or output characteristics of a combinational circuit. So to simplify any Boolean expression, the second method is nothing but the gate level minimization. First method is Boolean algebra. Second method is nothing but the gate level minimization. To understanding the working principle of a combinational circuit, we should analyze it. So first, to design any logic circuit, any combinational circuit, we have to analyze it. So therefore, we should first form a logic function between inputs and outputs. So we have to form a logic function, the relation between input and output. So using that, we have to form a truth table. So third step is we need to form a truth table. So a truth table is a table which shows the relation between input and output. So for each and every input combination, what will be the output? So the the truth table will give the information about the relation between input and output, and the last step is nothing but the final step in analysis is representing the combinational circuit by less elements, which is nothing but called as gate level minimization. So after truth table, we have to minimize the logic function. So using K-maps, we will minimize this gate. So this is one example how we can minimize. After minimizing K-map, so we will draw the logic diagram. This is the logic diagram. So for this logic gate level circuit, we will write the VHDL code. So here we have two gates, AND gates and OR gate, and we have one more NOT gate. So library declaration, package declaration, and entity, we have two inputs, X and Y. So X and Y are only single bit, so in STD logic, and Y in STD logic, and we have only one output, Z is output bit. So the relation between input and output, Z is nothing but Z equivalent to X bar Y plus X and Y. So Z equal to not X and Y or X and Y. This is the output equation. This is nothing but a design flow. We are writing the statement using concurrent signal assignment statement. So this is an example for data flow modeling of VHDL. So thank you so much. In this video lecture, I explained how we can design a combinational circuit. So what are the different laws in Boolean algebra, and how we can write a VHDL code in gate level minimization. Thank you for watching.